In this module, after learning about the introduction to searching and sorting, after learning about different searching techniques such as linear search and binary search, then after looking to the basic sorting techniques such as selection sort, bubble sort, and insertion sort, now next we are moving to learn about more advanced type of sorts. And these advanced type of sorts will include merge sort, quick sort, and heap sort. We'll look into each of these one by one. Let's begin with learning about merge sort next. So in order to learn about merge sort, first we need to learn about some of the prereqs. There are two main concepts to understand as prereqs. First is the concept of divide and conquer. This is the algorithmic technique that's used in many different algorithms. We'll look more into what does this divide and conquer technique mean and how do we use that technique into our algorithms. We'll design the merge sort algorithm that uses divide and conquer technique. Also, in order to understand merge sort, we need to just touch briefly the concept of recursion, but we'll actually look more deep into the concept of recursion in our next module. In here, we just need to remember that recursion, we need to know the definition of recursion. Recursion is defined as a function calling itself within it. So if we have a function a that's taking some parameters as input, it's doing something, we will be calling that function a within the function itself. It's not much different from function a calling function b within function a, but it's operated the same way as one function would call another function inside it. But the only difference is rather than calling some other function b, this function is calling itself. So the call stack is accordingly modified. And whenever we call, another thing to remember in recursion, because we are calling function within itself, another two things to remember is we should have some kind of base case, which is a case to exit, right? Otherwise, imagine this as a scope that's coming one out from the other. If there is no end to such a scope, from a bigger box, you'll have a smaller box and then a smaller box and then a smaller box and so on. If there is no end to that, this will just keep on going until infinite time. So in order to put an end to that, we'll have some base case that puts an end to that. So base case is some condition that says, okay, if this condition is true, then exit this recursion. And the other thing, the arguments that you are passing to the function when you are calling it within itself, that will be different from the original argument. So if the original arguments are a and b, there is no point of calling the function with the same arguments because the function will exactly do the same thing again. So you won't make progress towards your output, but rather you are repeating and doing the same thing in a circle again and again. There's no point of doing something like that. So in order to ensure that we are not roaming in a circle, but we are making progress to our output, we'll ensure that the arguments of the function, when we call within itself, the arguments are different. So this might be A2 and B2, the arguments. They're different from the original arguments of the function from where it started. So this is that we need to know about recursion for now. We'll learn recursion, as I just said, in our next module. But let's learn more about divide and conquer technique. So divide and conquer. As the name says, divide the thing. If you have a big thing, divide it into multiple small things and keep dividing until you are at a stage where you know the solution of the small set of problem. Once you are able to solve that small problem, then conquer by applying that solution to one step up. So we can see to this as, let's say we have a problem of size n, then as the divide and conquer technique says divide, we divide this problem of size n into two subproblems. Subproblem that goes from size 1 to n by 2, and another subproblem that goes from size n by 2 to n. We are dividing the problem of size n into two subproblems. Then we keep doing such division again and again. Let me use the same color. We keep doing such division. So you keep dividing the problem into the subproblem, subproblem into the sub-subproblem, then sub-sub-subproblem, and so on, until you reach a space where you have a solution to subproblem. So let's say after we divided the problem of size n into two subproblems of size n by 2, so from 1 to n by 2 and n by 2 to n, magically we know the solution for this size of the problem from 1 to n by 2. Then in that case, we don't need to divide it further because we know the solution of that subproblem size. So until we find the solution to the subproblem, we'll keep dividing it. Once we find the solution to the subproblem, both the subproblems, let's call this as subproblem 1 and subproblem 2. So once you find the solution to the subproblem 1 and a solution to subproblem 2, then you apply conquer. So then you apply the step of, here you divide it, next you apply the step of conquer. And what you do in conquer is combine the solutions of the subproblem in such a way to find the solution of your original problem. So what we are doing is, by conquering, we are finding a solution to the original problem. This is the concept of divide and conquer, where you are given a problem of size n. You take that problem, you divide it into smaller problems, and you keep dividing these things into smaller problems again and again until you reach a stage where you know the solution of that smaller problems that you have created. Once you know the state of these smaller problem solutions, then you conquer by combining these solutions one by one, and you keep combining the solutions until you are able to find the solution to the original problem directly. So let's look this more in terms of sorting and how does it relate to our sorting. Let's take the example and look into this further. So shall we use the same example that we have been using for our basic sorts? Why to change, right? If we can use the same, let's use the same. If you want to change, you are all feel free to change the example. 89, 45. We have 7 elements in this example, 90, 29, 34, and 17. 0, 1, 2, 3, 4, 5, 6. So applying the concept of divide and conquer technique that we have just seen here, when let's say we divide this problem into two subproblems. Now, because our array size is a odd number, it has 7 elements, one of our subproblem will have one more element compared to the other. Doesn't matter. It's still two subproblems. So we divide it into the two subproblems, and let's imagine that we have two separate arrays where you have the first 4 elements in the first array and you have the last 3 elements in the second array. Now, in order to conquer, we need to first find a solution to the subproblem. So what is the problem here is sorting. We want things to be sorted. Is this subproblem sorted? Do you see these things as sorted? This individual arrays of 4 items and 3 items, they are not sorted yet. Because they are not sorted, we'll further divide it into smaller problems again. Now this array contains 4 elements. We can divide it into the subproblem of size of 2, 68 and 90. This array contains 3 elements. We can divide it into subproblems of size of 2 and size of 1. Now, is this elements sorted? So now you have 4 arrays. Do you think these arrays are sorted? Well, for those that have 2 elements, it's not yet sorted. So that's why whenever you have 2 elements, you further divide the problem to one more stage to the size of 1. 29, 34, 17 is just one element, it's sorted by itself. You don't have to divide 17 any further. You can't break single number anymore, right? It's just a single number. So now you have divided, you are done with the step of division, the one in green, you are done with those green steps. Now comes the red step. Now, why do I say that we are in the red step is because at this stage, we know that our subproblems are solved. 89 by itself is sorted. 45 by itself is sorted, right? If 45 is the only number in the array, it's sorted. Our problem is sorting. And these subproblems that we have now, all the subproblems are solved by itself. So now we are at this stage where we have a solution to our subproblems. Because we have a solution to our subproblems, we move on to the second step of conquering. In conquering, here we need to merge our sub-solutions in a way to solve the original problem itself. And how we do that? Because we have multiple hierarchy of things. First, we merge these solutions to find a solution at this stage. Then we'll merge these solutions to find a solution at this stage. And finally, we'll merge these solutions to find a solution at this stage. So we will solve one by one stage. How do we do that? Is one of the simple way of doing that will be take these 2 items and whichever is smaller item in this, arrange them in a sorted order. How do you do that? Because there are only 2 items, we can directly say that compare 89 and 45 and keep the smaller item on the left and bigger item on the right. Similarly, you can do the same thing for the rest of the pairs, and 17 is already sorted. But this is not the generic way of solving. If you think what can be more generic way, because later when you want to apply the same solution to merge or to conquer this step into this step, then there'll be more items, more than two items, and then you cannot just compare like the pair of 45 and 89 and the pair of 68 and 90. You cannot just compare them. If we, even if you have these two sorted, so if you have 45 and 89 are sorted and 68 and 90 are sorted, you don't want to merge them directly too, like 45, 89, 68 and 90. This is not the correct answer. This is not sorted. So the solution that we find for the conquer step is very important. That solution needs to be generally applicable to the hierarchy of problem. This is 68. And yeah. So in order to find the solution for our sorting problem, let's say what we do is we initialize three index. We say that I'm maintaining index I for my first array. This array can be of any length. I'm maintaining index j for my second array. You'll be iterating using this index ID, and you are maintaining index k for the resultant array. Now, what you are doing is you are comparing the element I. Let's call this as L. Let's call this as R. So we are comparing L of I with R of J. Whichever is smaller between L of I and R of J, we will copy that to, let's say this as your final array, where we can say that as the resultant of your both the arrays. So let's call this as A itself. So we'll copy the item that's smaller among these both into your A. So now when you compare 68 and 89, 68 is smaller, so you copy 68 over here. And once you are done with that, for whichever item you moved, because you moved 68 to the final array, you increase the index of that array. So now J, because you moved it from R, so J increases by 1, but the I is still the same because you didn't touch that element. Then you again compare L of I and you compare R of J. Whichever is smaller, you move it to the array final array A. So here your 89 is smaller than 90, so you will move 89. Once you have moved 89, you will increment that index. So now I is incremented. This is I, not J, sorry. So now I is incremented. Then you again compare L of I and L of J, whichever is smaller, you move it to the final array. In order for this to apply, you have to apply from the bottom. So here are 89 and 45 are not sorted, and that's the reason our result won't work. So we need to apply our algorithm from the last layer of solution. So we cannot directly start from between, but rather we need to start from here. So I is this, J is this, and K is this. First, we start merging from the lastmost layer. And we say that whichever is smaller, move that to the final array, A, L, and R. From this, 45 is smaller, so we'll move 45 first, and then we'll increment J if there are other elements, because there are no other elements, so we are done. Finally, when one of the index reaches the end, like the J is done over here, there is no more elements in R after we move 45, then we copy the remaining elements of the other array. So here L is the other array, you copy the remaining elements of that. Because there is only one more element, we copied 89 there. After we are done with this first step, let's do the first step for even the other side. Your I, L, R, A. Whichever is smaller, move it first. So if we'll move 68, 68 is already there. And then once we are done with the end of any one array, we'll copy the remaining elements of the second one. So 90 will move. And we are done with this. We are done with the last step of both. Then let's move one step ahead. So now here, after we are done, we have 45 and 89. And okay, so then we move one step up. Then we say our L is this, our R is this, and now we'll get something that's correct, right? Because now when we are merging, we are merging two sorted arrays, 2 into K. So we compare L of I, R of J, whichever is smaller. Remember, our L of I is the one that's in red. We modified and we have this now. It's not the original one. So our L of I is 45. L of R is 68. Because 45 is smaller, we move it there. We increment our I. Then we compare 89 and 68. 68 is smaller, we'll move it there and we'll increment our J. Then we compare 89 and 90. 89 is smaller, we move it up. And we are done with the array, one of the array, we are done with L. When we are moving the elements from two arrays, observe that one array will be done faster than the other, right? Once we reach into that situation where one array is done, then we just have to copy the elements from the other array. So here, luckily, there's only one more element, so we copy 90 from that other array. And that's it. We are done with this step. Then we do the same thing for our right-hand side elements. So here, first we start with something, the last step again. So I and J, and this is your K, where because there are only two elements, you move them and 29 and 34 will remain in the same space even after moving. Then you merge or you conquer the step of 29, 34, and 17, where you have your I, J, and K. This is your L, this is your R. You compare L of I, which is 29, with R of J, which is 17. Because 17 is smaller, you move R of J to A of K. And then you increment your J, because there are no more elements. You are done with J. So you'll be just incrementing the K, and you will copy everything that's remaining in the other array, that is L, to the array A by using your K index. So you're incrementing I and you're incrementing K. Two things you are incrementing and you're copying all the elements. So first we'll copy 29 and then we'll copy 34. We are done with this step. Then finally we have our this as well as this, right and left hand side. We have solution to both these sub-problems. Now, because we have solution to both these sub-problems, we are exactly at this stage. We know a solution to our sub-problem, and we know our solution to our sub-problem 1, and we know our solution to our sub-problem 2 as well. Because we are at that stage, finally, let's go ahead and conquer the solution to our original problem. So again, we'll do the same thing we'll repeat the same step of conquer, but just remember that our new array is this now. This is what we are working on. And the older elements, we have just overwritten them on top of them in the same memory location. So they doesn't exist anymore. So let's take these two sub-problems. Take the same way, take your index I, take your index J, take your index K. What we are doing is again merging two sorted array into a final sorted array. How we do that is element wise. So first we compare L, R. So we compare L of I and R of J. Whichever is smaller, we move it into A of K. So here we'll be moving 17 first. Because we moved 17, we will increment our k and will increment our j. So now k comes here and j comes here. Then we compare 45 and 29. 29 is smaller, we move it here. And then again, we increment our k and we increment our j. Then we compare 45 and 34. 34 is smaller, so we move it here at the third position. And again, we increment our k and we increment our j. Can we increment j further? We cannot because we have reached the end of array R. There is no more j. The length of R is done. Once we reach an end of any one of the array, we'll copy the remaining elements from another array just into our array A. So here, this copy, we don't need to compare now anymore because we know that our subproblem is already sorted, right? So everything that exists in our subproblem is sorted. We can directly just copy that. So we'll copy our L of I into L of K by incrementing both the index at every iteration. So in this copy, we'll first copy 45, then we'll increment our K, we'll increment our I, and then we'll copy 68. Again, we'll increment our K and increment our I, and then we'll copy 89, and then we'll increment our, again, the last time, we'll increment our K and increment our I, and finally we'll copy 90. And then we reach the end of the size of the array L, and that's it, we are done. So now when you see this array, the one in red that is sorted, we are done. So this is how we apply the technique of divide and conquer to the problem of sorting. And this algorithm that came by application of the technique of divide and conquer to the problem of sorting, this is exactly what's called merge sort. So what we did here is merge sort. Are you ready to implement the pseudocode for the merge sort? Let's have fun with implementing and making our pseudocode with that. So if you have understood that example correctly now, what we were doing is we were having different functions. First, we need to have the function to process our merge, right? Merge is our conquer step, where we are combining two sorted subproblems into a sorted original problem. That's our merge step, and merge is the conquer that we are doing. How do we implement this merge step? What we had in the same way, we'll take three iterating variables, I, J, and K. We have our R, we have our L, we have our R, and we have our A. So what we were doing while we were merging these elements, let's trace those steps into a pseudocode. So our merge algorithm, what are the input that our merge pseudocode will take? What do you need as input for merge? You would need your left array, your right array, and the original array, A, right? You will need your two subproblems and you will need your original space. So let's take L as your left sub array, R as your, let's write array, array L, array R, and array A. And if you want, you can also take, the size of L, let's call it NL, the size of R, NR, and the size of A, which is NA. Once you know these all things, we can also compute these sizes, as I mentioned earlier, within your program. So even if you don't have them as your arguments, You can have steps to compute the sizes, such as the steps can be represented in your pseudocode, such as NL is equal to length of L. I think by now, after if you have watched all the previous modules properly, then you should know how to compute the size of an array in C++. So that's exactly the syntax that you'll apply here to compute the size of your L. Then you have your array L, and R, which is an int, will be equal to length of R, and A is NL plus NR, right? So we don't need to compute that. Then you will initialize three variables, I, J, K. Let's set them to 0 initially. All are 0. And then we'll enter into our while loop. Now, before we start writing pseudocode, let's just take a step back and think how we want this loop to be designed. So while we were doing this example, what were we doing? We were having one loop that goes through, we are having, let's make this case simplified. Let's say, let's talk about just the last step of this so that it's more clear. So let's say our array is this 89, 45, 68, 90, 29, 34, 17. And let's say we have these two subproblems where we have reached the step of conquer at this step where you have two subproblems that are already sorted. That's what we are tackling in merge, right? So these two subproblems will be 45, 68, 89, 90. And after conquering, these two subproblems are 17, 29, 34. We assume that we have already done the steps below. But just for the sake of the example, we are taking these two subproblems. These two subproblems are already sorted. And what we want to do in this algorithm that we are writing, the merge algorithm, is we want to combine these two sorted subproblems into original subproblem. So what we are doing logically is we need to iterate. We took these three variables, I, J, and K. This is our A, this is our L, this is our R. We know the length of L and R, so we are iterating I from I equals to 0 to NL minus 1, if NL is the length of L, and J equals to 0 to NR minus 1, where NR is the length of R. We are iterating these variables from this to this. And what we are doing now, as you see that there are two iterations already. So these two iterations can be two for loops or two while loops. And then each loop, what we are doing is we are copying, we are comparing, we are doing some comparisons. And depending on the result of our comparisons, we'll be copying the element into our array A as a result of our comparisons. So this is your first while loop. In first while loop, you'll be iterating through both the arrays and you'll be incrementing your index until you reach the end. And you'll be, depending on your results of comparison, you'll be copying that into your final array. Then what will happen is you will reach end of one of your subproblems. So here, as in this case, we reached, in this example, we have already traced it. So we know we reached the end of our R array way before we even started copying elements of L. So elements of L were still left when we already reached the end of R. In that case, where once we reach end of one of the sub-array, then after that, we copied the remaining elements of the array that has still more elements to the original problem directly. So we copied these for 45, 68, 89, and 90 to our original array afterwards. So this could be imagined as another while loop or for loop, where the first while loop or for loop has a condition that until you reach end of one of the array. Once that is done, that loop is completed and that loop will be exited. Then second, you can have a loop for the array in which still there are remaining elements to copy that remaining elements from that array to the original. Now, I assume you all are smart enough to understand that in this example, we have some of the elements left in our L array, but you can perfectly frame another example where the elements will be left in your R array, right? And both things can happen in the same example at multiple stages as well. So we'll have two loops. One, if the elements are left in the L array, then we'll copy the elements of that to the original array. If the elements are left in the R array, that's your third loop, then you'll copy the elements from the R to the original array. So in total, we have thought that we need three loops. The first loop goes from I 0 to NL until your I is less than NL and your J is less than NL. Notice that we have AND. So both these needs to be true. That's your first loop. As soon as one of this is done with its length, with its element, then one of it will be violated. Here your J less than NL condition got violated first in this example at this stage. That's your first loop. Your second loop is copying the remaining element of I. So this loop will be I less than NL. And you are not resetting your I to 0 at this step. So wherever your I was, here our I was it's 0 itself when that stage was reached. But your I can be somewhere in between too. And because you are not resetting, you are just taking your remaining elements from there and then copying it to the original array. So that's your second loop. And your third loop, it can be your array R that has remaining elements. So in that case, then you will take the remaining elements from wherever the J is at that time. It can be 0, it can be 1, it can be 2, it can be anywhere. The remaining elements of that array R, you take those and you copy that into original array. So until you reach the end of the array. So these are your three loops that you need to consider while designing the pseudocode. Understood? Now let's go back and flush down our pseudocode. We are almost there. So our first loop, while I is less than NL and J is less than NR, we need to do some comparison. If your L of I is less than equal to R of J, okay, I'm just rechecking my internet connection. So if your L of I is less than equal to R of J, in that case, what you want to do is move your L of I to A of K. In order to do that, you need to have A of K is equal to L of I because your L of I is smaller. And then you definitely need to increment both the index. So I is equal to I plus 1 and K is equal to K plus 1. Because you moved an element from I, you are incrementing I, and K will obviously you need to increment to the next position. Else, if your L of I is not less than equal to R of J, but if it's the reverse way where your R of J is less than L of I, then you will move the element from R of J to A of K. So you'll have similar step where your A of K is equal to R of J. And then you will increment your J is equal to J plus 1. And you will also increment your K. I'm just writing it here in the same line, K is equal to K plus 1. And that's it. So you are done with your first while loop here. After this first while loop, you'll be done with all the comparisons that you need to do. After this first while loop exit, you will be left in a condition where one of the array will be done with its element, either L or R. Any one will be done first, and remaining array will have some remaining elements. In that case, because the remaining elements of any single array is already sorted, you are taking the sorted subproblem. You are taking the subproblem that's already solved. You just need to copy that to the main array. And that can happen for L or R. So we'll have two loops. So let's continue our algorithm here. Next, we'll have another while loop. While we are not resetting our I, observe that. If you reset your I, then you have no more a concept of copying just the remaining elements, right? That's what you don't want to copy all the elements of any array. You want to just copy the remaining elements. So after your first loop is over, your I and J are at some position, and then only the remaining elements from that position is what you want to copy. That's where we don't reset our I and J, but what we do is while I is less than NL, then A of k is equal to L of I, and increment I is equal to I plus 1, k is equal to k plus 1. Or what you will do is, while j is less than nr, increment copy A of k is equal to r of j, and then increment your j is equal to j plus 1 and k is equal to k plus 1. And that's it. So you are done with your 3 while loops that we need to implement this application or this algorithm of merge. Remember, this is just the merge. Still, we have not completed whole MergeSort. We have just figured out how to take two solved subproblems and combine them into how to take two sorted arrays and combine them into a single sorted array. So this is halfway there. We are done with the conquer step. Now, how do we do the whole MergeSort? Let's write. And so in the MergeSort, now the step that's remaining is your divide, right? You are done with solving the conquer. Divide is the step that's remaining. So let's write that algorithm, MergeSort. This is your cumulative algorithm in which you divide, 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 and then finally we'll call merge at some point to combine. Once you find the solutions of the subproblems, you will be calling merge. So this is your final MergeSort function. As an input to this overall MergeSort function, what you have is array A, and you can have the size of that array A, that's NA or N. Let's begin. So first, as you know, in order to do the MergeSort, we are using the divide and conquer technique. In order to use divide and conquer technique, you definitely need to divide first, right? And when you are dividing things, you can divide things only up to a point when there is just one thing. If there is only one element, there is no further way in which you can divide that element. So we have that condition. If your n is less than equal to 1, then you just return. That's your first condition. Otherwise, if that's not true, then else you say you have a variable mid that's equal to n by 2. That's your an. That's your size of your a or na. Sorry about that. Na, na. Else, now you need to, if there is not a single, just a single element, then well, you have more than one elements, where if your length of A is greater than one still, in that case, you further need to divide that. How you divide that is by the midpoint, half in the L and half in the R. In order to divide it by the midpoint, you say mid is equal to NA by 2. And then you say copy the element. So the left is equal to, or let's say NL is equal to array of size mid, right? From your 0 to mid, 0 to n by 2 is your NL, and your NR is equal to array of size n minus mid. That's your remaining elements from your n by 2 plus 1 until n. Then these are just NL and NR are just the size of your left array and right array. You've got that, but you're not still done. You need to copy all the elements from the original array A into your L and into your R in order to make these arrays. So this is the divide step that we are doing here. In order to do that, we can use for loop, and we can say for loop iterating from I equals to 0 to mid. In this for loop, copy, say L of I is equal to A of I and increment I. So in this way, you can copy all the elements, that is from 0 to mid into L. In the same way, you'll have another for loop for I is equal to mid to n minus 1, where when you are writing C++ code, you will either use mid into your L array, or and then if you are using mid into your, if you are iterating your first iteration from 0 to less than mid, then the second iteration will be from mid to less than n minus 1. But if you are iterating your first iteration from 0 to mid, then your second iteration will be from mid plus 1 to n. There are multiple ways on which you can choose to do things, and that's why a single application can have multiple programs solving that application. Some programs can be more efficient, some programs can be less efficient, and some programs can be just say equally efficient but designed in different ways. And these are your different assumptions and design choices. So if we choose our first loop from I equals to 0 to mid minus 1, then your second loop will be from mid, which is the next element of mid minus 1 until n minus 1. And we'll say that in this loop, say R of I, which is your mid, R of I is equal to your mid, is equal to A of I. If when we use R of I, okay, let's rethink this. If you use R of I, because if this is your right element, your I is something in between. So let's say for this example, your mid from 0 to mid, where your n is equal to 7, then when your n is equal to 7, 7 by 2, so that's 3. So from 0 to 1, 2, 3. From 0 to 3, you will be copying our L. That's your first for loop over here. This loop will be doing that. Then in the second loop, you want to copy these elements from 4, 5, and 6, which is your I now, to R of, you don't want to copy to R of 4, 5, and 6, but rather you want to copy to the R of 0, 1, and 2. And that's why we wouldn't have just R of I is equal to A of I, because if you have just R of I equals to A of I, it will copy to R of 4, 5, and 6. We don't want to make our array R like that. We want to start our array R from 0. That's why we won't have just R of I is equal to A of I, but we'll have R of I minus mid. R of I minus mid, what it will give you is your mid is 3, right? Your mid is equal to 3, where your I would be 4 in your second loop. So 4 minus 3 is equal to 1. R of I minus mid, your I is 4 for sure. No, your I is equal to mid. So your I is equal to 3. Your I is equal to mid. So your I is equal to 3. And what we are doing is I minus mid. I is equal to mid. So I is 3. 3 minus 3 is equal to 0. And that's how we'll get the 0 index. Whenever you are writing your own pseudocode, it's very important to verify the small things here and there. I'm framing this pseudocode right now with you. And that's why I am doing the exact thought process, which I want you to do when you frame your own pseudocode. And as I said earlier, there can be multiple ways of doing the same thing, multiple correct ways of doing the same thing. But whatever way you follow, just think it through in the same way as we are thinking it together now. So R of I minus mid is equal to A of I. That will frame your R array all correctly. Once you are done with that, then you have your L array, you have your R array, you are done with your divide step. And you will be dividing until you reach a stage that the subproblem is solved, right? How we did in our example, we didn't divide it once and we set back, because after we divided once, then we still didn't have our solution ready. Rather, I'm waiting for my screen to move. It's a bit of lag there. So after we divided our array once, there it goes after a lag. So after we divided our array once, then we didn't have our solution right there, but rather we had to divide it again and then divide it again. That's what we did here while we were solving this whole problem, right? Dividing again and again and again and again until you reach a stage where there is only one element, and we know one element by itself is already sorted. So in order to do this divide step again and again, that's exactly why we need to call our MergeSort function recursively. If you remember at the beginning of this lecture, I said the two concepts, one is divide and conquer, and second is recursion. We will call our MergeSort recursively, that is calling the function within the function itself. So MergeSort is our function. We are calling it within itself, MergeSort, and we are saying that our when we call our function within itself, we don't want to pass the arguments that's same as the original function. So the arguments of our original function is array of size a and int n. That's the size array a and the size of a. But rather, when we call function recursively, we want to move towards the solution. So in this case, as you have seen in the example, first we had elements, the array of size 7. We divided into array of size 4 and array of size 3. And then we took the input as array of size 4. And we further divided into array of size 2 and 2. So the next time when we call MergeSort recursively, as we are taking the input of array of size 4 there, that's nothing but our left array. So we are calling MergeSort on our left array, and we are passing L and NL as our arguments. We also, whatever we do for our left hand side of our divide tree, we also need to do for our right hand side, right? The same steps we did for left and right both. So we'll also call merge sort again recursively for our right side tree where LR and NR are the arguments we'll pass. Now, there was another most important thing I said while we are using recursive function, we need to be careful of. Another thing was having the base case. In this case, what is our base case? Our base case is something that says our recursive function that exit from yourself. You are done. You have your answer there. In this case, our base case is this step over here, where if whenever the size of the array is less than equal to 1, then it will exit the recursion. So it will keep calling the function again and again. First we had array of size A, then we had array of size um, 4, 7, then 4, then 2, then 1. It will keep calling it again and again until the size is less than equal to 1. So finally, when you have array of size 1, that's when this divide step will stop. So that's when the recursive calling will return. The recursive calling can be also imagined as a stack. So where you first put your first function. So first we are putting f of a, then f of a is calling f of l and f of r. And then f of l is further calling 2, right? Its own f of L1, let's say that, and f of L2. And then after that, f of r is calling its own f of r1, f of r2, and so on and so forth. So that is your recursive stack. Finally, once you find the solution to f of r1, f of r2, that will return. So that will pop, that will pop. Once these both pop, once you have an answer of L1 and L2, you'll have and R1 and R2, then you will have answer for R, then you'll have answer for L. Once you have answer for your R and L, then you'll have answer for A as well. So that's how the recursive function stack is called, and it returns in a scoping rule. We'll further discuss recursive function much more in detail in our next module. For now, this is sufficient for us to understand and proceed. So we are calling our MergeSort function to do that recursive division on our left sub array and on our right sub array. Are we done? No, we are not yet done. We are just doing the divide step. Finally, after these functions are recursively called, when it comes to a stage where there is only just one element, that step of recursion, it will return from this step. Once it returns from this step, we need to start the conquer step where you merge first two individual integers into one, and then and once you have the pairs of 2, then you merge those into 4, and then you merge 4 and 3 into 7, right? So once we once we divide until the step of having just the one integer, it will keep calling the divide recursively. And once we reach there, this if condition will be violated, where your length of the array that's passed to this function as an argument, either L or R, that won't be any more less than, that won't be any more greater than 1. Because it's not greater than 1, it will be less than equal to 1, so it will return. Once that returns, then we need to do merge. So at that time, in order to do merge, then finally we need to call merge call. We have already implemented our merge function. This merge call is on left, which is your L, R, and you are using in as a merge call, in the merge function, you are passing array L, array R, and array A as your argument. So that's exactly what you pass from here, array L, array R, and array A. That's it. So with this, you are done with your MergeSort implementation. Finally, let's look at the time complexity and space complexity of MergeSort. The time complexity of MergeSort, if we look at the steps that we are doing in the MergeSort, we are dividing things into two, right? And every time you are dividing things into two, and further you are dividing that into terms of two, you can process these things in parallel. You can process your L and R in parallel. And that's where the total number of steps that you are doing, that will be height of your tree. That's not proportional to n. If you have 4 elements in your array, the height of your tree that you frame by dividing wouldn't be equal to 4, but rather the height of the tree will be equal to log n, will be proportional to log n. That's the steps that you are doing while you are processing MergeSort. And that gives you the idea that the complexity of MergeSort is not is something in sense of log n. How exactly? Let's look at that. So initially for these steps that are the if condition, the mid assignment, the N and L, let's call that these steps are simplistic steps and they are not doing any loop, right? So these steps takes cost C1. And then we have this for loop that iterates from 0 to mid minus 1. And we have another for loop that iterates from mid to n minus 1. So both these for loop will cumulately iterate through size n. And we can say that gives us cost C multiplied by n because it's iterating through size n in total. These steps, let's say the cost of your MergeSort is T of n, and you are finding the cost equation for that. So MergeSort on an L equation, which is half of your T of n, right? Your L is half. That will be T of n by 2, and your R will also be almost T of n by 2. There can be plus or minus one element in these, but that are constant, doesn't matter. We are finding the big O cost. The cost of your merge function, which is whole independent function by itself over here, the cost of the merge function can again be looked in the same way, where you say that these are the cost of these constant steps is C3. The cost of all these three while loop, it's cumulatively iterating over size n. So you can say that's C4 into n. And that's where the cost of the merge function can be written as C4 into n plus C3. So in total, you can write the cost of your Tn function as 2Tn by 2 plus C2 plus C4 into n plus C1 plus C3. So these are constants, and you have the recurrence term here. If you replace the equation for this recurrence term again and again, the second equation you would get is T of n is equal to 2 times T of n by 2 plus C of n. Let's replace the constant with C and then neglect the constant terms. And so on and so forth. Keep replacing your T of n term. If you keep replacing your T of n term, then you will end up into a situation where it's 2 into further 2 times of your T of n by 4 plus Cn plus Cn, and that's equal to 4 times T of n by 4 plus 2 Cn cumulatively, and so on and so forth. So you can say that finally you can replace, if you replace 4 here with some term to the power k, then you can have the expression in terms of 2 to the power k and to the power n divided by 2 to the power k plus k multiplied by c times n. And then If your n is equal to 2 to the power k, that's the replacement that we did over here, your k is equal to nothing but 2 log to the base 2 of n. So this expression will become 2 to the power log to the base 2 of n t of 1 plus log to the base 2 of n multiplied by c into n. And here, this in this expression, from here you can, if you remove the constant, it's of the order of n log n. And this 2 to the power log 2 to the power 2 log 2 base n, that's nothing but n. In between n and n log n is greater. So we say the big O time complexity of MergeSort is big O of n log n. Finally, the space complexity of MergeSort, which is the auxiliary space that MergeSort takes, it is not in place algorithm. And the additional auxiliary space that the MergeSort takes is equal to something more, because every time we are dividing an array, we are using some more space. So if you look at the tree of when we are dividing the items, how much additional space that we are using while you are processing MergeSort, that additional space could be in worst case of the order of log O of n, even when you consider that you are deleting the space that is no more needed. So the space complexity of MergeSort can be of the order of big O of n. That's it. Next, we'll look into quicksort in our next lecture. If you have any questions, please see me in my office hours. Thank you.